Thank you very much. So I'm going to be demoing and talking about this sort of experimental project we have been working on throughout the spring. But before I say anything more, I'm just going to show you how it works, basically. I'm going to need to connect to the sound as well. That's going to be vital to this. Do we have sound?
A soft language spoken in movement and electronic song.
Take me to the jungle.
Hear the jungle's breath in the drone. Trace its humid pulse through the rustling leaves.
So what this is a kind of soundscape that you can talk to. You can ask it questions, tell it what you would like to hear or how you're feeling, like where you would like to be, and it'll kind of attempt to create a sound world for you to listen to that somehow is connected to what you just said. And it also gives you this little sort of meditative utterance back, which is designed to sort of make you listen to it more deeply. It's kind of a prompt back to you to kind of listen to it. So it's sort of a kind of a relaxation app in a way. It's like meant for slowing down and listening to things. And everything we are listening to here is generated with generative audio model that I'm going to talk about. So every sound that you hear comes from, isn't actually recorded, it's generated. And so today what I want to do is kind of do a like technical walkthrough of what actually happens when I do what I just did. And so in many ways this project has been sort of an experiment in doing as much as possible using like various AI models. So I'm going to just continue that ethos as I kind of present this technology. I'm going to use Cursor Agent as my co-presenter, which does put me in a situation where I don't actually know what I'm going to talk about in a few moments' time, because every time I do this, it becomes a different talk. So let's just hope this is one of the better ones that we're going to get today. At least we'll have something nice to listen to, because I've also given the Soundscape to Cursor as a model context protocol server to have it basically create soundtracks for what it's doing based on what it thinks that these things sound like. So what I'm going to try to do first is set this off, generating an architectural diagram for us that will describe the kind of process from prompting to the response that the model gives us. And I'm ideally going to use Claude 4 Opus for this. It came out a few days ago, and I think the majority of that time it's been over capacity, so it mostly just fails, but let's see if it works this time. Seems to be doing something. It's now designing a soundscape for us to listen to while it's designing an architectural diagram. While it's doing that, I'm just gonna give you a bit of the lay of the land here. So this is a web app, has a front end built in Next.js that runs the UI. in the browser, and it has, as part of that front end, this kind of audio playback engine that's written in C, that has a bunch of effects and stuff that's mixing the Soundscape live. And this is compiled down into WebAssembly, and it's running there in the browser continuously and playing back these various layers of sound. And then we have a backend, which is a BUN server that is running on a VPS on DigitalOcean, where we are doing lots of the kind of coordination behind the actual generation processing. So Claude is busy kind of studying our code base still here. Should be ready in a moment, and hopefully give me some material, because I don't have any before I started. So basically going on here is I have this MCP that's commanding the sort of server that I have running, which then pipes the sound back into the browser to this app that I'm just playing here. And it's been kind of interesting to have kind of a coding soundtrack as well, like have your IDE basically generate ambient music for you based on your coding tasks. There we go. This is what happens every time with Claude now. Let's see if OpenAI can say what they can. Never took this long in practice. Right, so we have something that's hopefully going to be a diagram. It seems to be one. There we go. So let's study this a little bit. Let's see if it's going to be complete slop or not. All right, so the first thing we actually do here is when you click on that button to open the microphone, what we're doing is we have a problem to get audio, and we need text from that. So we are running this kind of transcription service actually in the browser that is using a service called DeepGram, which opens a WebSocket connection to our browser, and then we send the audio from the browser to there, and it gives us back in real time the text transcription of that audio. So it looks like this. We just import their SDK, and then we configure it. We say we want to use their model, and put in various parameters of what we send back to it, or what we send to it, and it sends back the kind of text of what was spoken. And then what comes out from that is now we have in text form the prompt. which we then send over to our backend. And here's where the actual work starts for us to actually turn this into a soundscape. So the first thing that this diagram is saying here is that there's a coordinator LLM deciding the new soundscape state. Now, what does that mean? So when I say something like, take me to the jungle, that actually isn't something that can yet be turned into audio. It's not really a proper audio prompt yet. We need something to kind of process that into something that can be generated. So to kind of help you understand what's going on there, I'm just going to ask this thing to show me what it does. So let's say we're going to tell the soundscape to play an alien artifact discovered deep in a woodland area. Let's use a better model for this, and then show me what it returns. So here we start to see that actually creates 4 different layers of sound. Which have these sort of detailed prompts like gentle wind rustling through ancient tree leaves, low resonant and slowly pulsating hum, high-pitched shimmering and slowly evolving alien tones, shifting drones. So that's kind of what happens behind the scenes. We take your sort of prompt and we turn it into this kind of more detailed soundscape. And I don't think we're actually hearing it, so let me see what's going on here. This thing is using the right session.
The deep hum holds the space. Let it resonate within.
Just going to run that again. And here you see what's going on as well. It's kind of turning these questions or these commands into specifications of soundscapes. So what we're doing with that is we have this kind of massive system prompt in the back end where we are convincing the model that it is a skilled, mysterious sound designer. And we have detailed instructions to it, for like what to do when it gets one of these user requests. And like what kinds of layers are possible for it to make, how it should interpret various things users might say, how to deal with volume control, how to kind of like basically construct these descriptions of audio prompts, which are essentially going to be the things that the audio get generated of. So that's important to get these right. And what we're using for this is pretty much the same thing as Charlie was just showing, Gemini. Gemini Flash 2.5. We are using the version they came out, which is last week at Google I/O, which is working pretty well. So what we're doing is we are feeding it this massive system prompt and the history of the session and the prompt from the user, and it does all this business of turning that into a specification for a soundscape. We didn't start out using Gemini for this. We actually started using Claude at first, which was great. It worked fine for this, but it's just quite slow and quite expensive to be doing these kinds of things with that. So we went into a whole side quest of like this, looking into these open source models like llamas and things like this, and they worked fine. But then when Gemini Flash came out, which is that kind of smaller flagship model, That's just almost as quick and almost as cheap as these open source small models are, but just much better. So we're using that now. So that gets us this sort of layer specification. That's of course not yet something you can listen to. That's just text. So we still have some work to do. So if we go back to our mermaid diagram here, there's some embedding stuff, which I'll talk about a little bit later, and caching that I'll talk about later. But first I want to cover this actual audio generation business. So what it says here is that we are requesting modal service to render audio. What this is in reference to is that our backend has a backend, which is written in Python, which we are running in this thing called modal, which is essentially a serverless platform for running Python code in, but it specializes in giving you GPUs attached to that Python code. So what you can do is you write some Python stuff, you specify the Docker images you want to run it in, your dependencies, and then the actual code, and it gives you a GPU attached to like a virtual machine that runs these as kind of serverless functions and bills you by the second for it, which is good for this kind of thing where we need to kind of be elastic and use as little or as much compute as we need. And we use a lot of stuff here, but the most important part is here with our audio generator, where we attach an NVIDIA L40S GPU and run this audio generation thing. And that thing is running a specific model called SAO, which is short for Stable Audio Open. So this is a audio diffusion model, an open source one, an open weights one, put out by Stability AI, which is the same company that also does stable diffusion for images. This is trained on basically public domain and Creative Commons data, mostly things like Soundscapes and things like the stuff we're listening to at the moment, basically. And it can give you up to 47 seconds of high quality audio based on a text prompt. And that's what we're doing for each of these audio prompts that we are generating. So this model takes a text prompt and some duration information, and it runs this kind of diffusion process where it starts by generating some random noise and then kind of incrementally filters that out into some sound that matches the prompt that was given. It's kind of the same process as you might be familiar with stable diffusion and things like that, where images are generated with this kind of process, but it's the exact same thing, just in the audio domain. And it works rather well. Basically, everything we hear now is filtered out from this kind of latent noise in this exact way. So when we get one of these things, we generate it on the modal service, then we upload it to our CDN, and then it gets fetched back by our front end into the browser, where the audio player then plays it back as a kind of infinite loop with some runtime processing on top to kind of make it nice. Now, that's all good. There's kind of one thing I wanted to mention here, which is that even though this this model works quite well, and it's quite fast actually as well. It can get kind of expensive to kind of run that every time someone wants a sound file, especially for this kind of thing, which we're going to put out on the web, and we're probably not going to ask people to pay for it. It's going to be like just a thing on the internet. So we don't want to like pay too much money to run it. So we are for that reason putting a lot of effort into caching as well. So because the thing is, when you want to hear something like the sound of birds or something like that, it's quite likely that someone at some point has already needed something quite similar, and we might have it in our database. We currently have about 20,000 files in there, so we kind of probably have something quite close to it already. And so what we're doing with that is we're using embeddings in our audio generation process. So when we have these prompts, we run this embedding model to basically get numeric vectors out of them, also quite similar to what Charlie was just showing, which put these audio prompts into this kind of abstract multidimensional space. They have an address somewhere in that space. And the idea is that when we need a prompt, we can look into its embedding and see if there are other embeddings somewhere close by in that space, because if there are, they are basically cache matches for us. So we're doing kind of semantic caching here. We're using this specific embedding model called CLAP for our embeddings. And this is an embedding model that is specialized in a sound. So it's trained on pairs of audio files and text descriptions of those audio files. And they are trained together to go into the kind of same embedding space, which means that things that are described kind of end up close by or far from each other based on not their semantic content, but what they actually sound like. So when there's some textual content, we get an address for what the phenomenon in that text sounds like. And that's perfect for us for doing cache lookups. So we're doing that for all our prompts. We're not doing anything with the audio side of the CLAP model. We're just embedding our text descriptions and doing like cache lookups based on that. So if we have something like sound of rain, we probably already have a very similar sound of rain, so we can find it from our cache that way. And if we do, we just use that instead of kind of going through the whole trouble of generating a new one. And I thought it might be a fun thing to try to look at what these embeddings actually look like and how they kind of visualize the space of sound that we have in here. So a visualizer would be nice for that, but I don't have one just yet. I just have a prompt for one. So the demo gods willing, we're gonna try to have it made for us here. And let's see if Opus is available for this. So I'm telling it to create a little visualization UI. I have, in our APIs, we have available these things called 3D UMAP embeddings. So what UMAP is basically when you have like a collection of embedding vectors, which are high dimensional, like 500 dimensional vectors, but you want to look at them as a human to kind of make sense of what they are. You run this kind of dimensionality reduction algorithm called UMAP, which kind of can get them down to 3 dimensions or maybe even 2 dimensions to give you a sense, intuitive sense of how they relate to each other while still retaining some of that, some of the structure. Claude is not going to be here, is he? Nope. Back to OpenAI it is then. Obviously, we first need a soundtrack for this work. I can also show you what they are doing. So what O3 thinks an embedding visualizer should sound like is a tranquil cosmic workspace. Let's see what we get. There we go. So here we have a space of about 20,000 points, each one representing a sound, one of the sounds that you are hearing, or many of them. Let me just try and also do the second part to make this interactive, so we can actually see which sounds they might be. So you can see that some sounds are close to each other, some are clustered together, some are far away, and this is based on clap. And the kind of idea is that things that sound similar are somewhere in there, and the whole universe of things that this thing can make is somewhere in here. So we have urban environments. For some reason, plane cabins are far away from everything else. Like bees are over here, and insects. Street ambience in this neighborhood. Railroads. And so on. It's kind of fun to think about all the sounds. So every sound we make here kind of is pulled from this space or gets generated and is added to this space as a new point that kind of describes some new sonic phenomenon. And I think that pretty much takes us through our process here. So what we do is you click a button, you speak to a microphone, that gets transcribed into text with a service called DeepGram. We send it to our backend. For processing, we run it through Gemini, which figures out what kind of soundscape that consists of, what kinds of layers should be in it, what combination would be good. And then we try to make that into sound. So anything new we need, we set into this modal service where we run stable audio open to generate new audio for that layer, and anything we might have already is pulled from our cache. And let's see if this thing can understand what a finished sauna sounds like. Finished sauna on a spaceship, which is quite specific. So yeah, this thing is also running downstairs in the foyer. So you can go and click on it and say something to the microphone and just see what it does. And when you do, all this thing will be happening in the background. So it'll call these various services, and lots of bits will be flying around on the internet to make that happen. And yeah, hope you'll give it a try. Kiitos.